Welcome to this demonstration for hypothesis testing for a single population mean. Our context for this example is Hamilton ACO, and specifically Hamilton ACO leadership is interested in better understanding spending on office-based visits by its beneficiary population in a given year. So the ACO has an analyst, and they have done some descriptive statistics where they've estimated the sample average spending to be $2,123 per year, with a standard deviation of $6,204 a year and a sample size of 3,185 beneficiaries. So here, there's a conjecture made that the average office visit spending per year is $2,000. And we are basically going to use our sample evidence or sample data to assess whether or not there is evidence to accept that hypothesis or to reject that hypothesis in favor of some alternative. So when we do hypothesis testing, of course, using the critical value method, we want to start by specifying our null and alternative hypotheses. So let's do that in this context. So to begin, this is a hypothesis test about a single population mean. So we're going to specify the null hypothesis around the population parameter mu, okay? Again, hypotheses are always about population parameters, never about sample statistics. So in this case, our status quo is that mu is equal to $2,000. That's essentially what we would assume to be true unless convinced otherwise. Our alternative in this case is that mu is not equal to $2,000. Perhaps we don't have any prior assumptions about whether it's higher or lower, so in this case we would leave it as a two-sided hypothesis test. Of course, if we did have some priors about directionality, we could specify it as an upper one-sided test, for example. All right, so we have our null and alternative hypotheses, and now we want to move to writing down our test statistic. So recall that for a hypothesis test for a single population mean in which the population variance is unknown, we're going to estimate that using our sample data. That leads us to having a test statistic that is distributed as a student's t-distribution. So let's write this down. Our test statistic is going to be equal to our point estimate of x bar minus the value of the mean under the null hypothesis divided by our measure of sampling variability, which is the standard error of the mean, using information about the sample standard deviation and the square root of the sample size. In this case, now let's substitute in our information and calculate our test statistic. So here we have $2,123, that's our point estimate, minus the value under the null hypothesis, which is $2,000, divided by 6,204 divided by the square root of 3,185. When I calculate that out, I get 123 divided by 109.93 for a test statistic of 1.119. So how do we know how to interpret this? Well, the next piece, of course, of this process is to identify the threshold or the bar for which our test statistic will be compared. And based on that, we will make a decision about whether there's evidence to reject the null hypothesis in favor of the alternative. Let's draw a picture to see what this looks like. All right. So here we have our famous t-distribution. Again, it is a symmetric distribution, a family of distributions that are centered around 0, and any particular t-distribution is defined by its degrees of freedom. Degrees of freedom in this case is just equal to the sample size minus 1. So we have a quite large sample here. Now, one thing I failed to start out with, but we're going to include right here, is that we always need to pick a significance level. That's going to determine our threshold for how we decide whether or not we have evidence. Remember that alpha, our significance level, is a type 1 error probability, and we want that to be quite small. In this case, I'm going to use a significance level of 0.05, which is a very conventional value to use in the social sciences. All right, so if we have our value of 0.05 and we're doing a two-sided test, we're going to look for the area or the value of t such that we have 0.025 in each tail. That's equal to alpha divided by 2. The area to the right in each of these tails and to the left represents the rejection regions. We're going to compare our test statistic to the values and to the critical values, which are delineated by these lines, to determine whether or not we have evidence. So let's figure out how we find our critical values here. If we were doing this in the old school style, we would use a textbook to arrive and look up the degrees of freedom and arrive at our value. In the modern era, and in the era of this class, we can also use Excel to do this. And specifically, we can use the .tinv function, where we will enter the probability and the degrees of freedom. And Excel will return to us the critical value. In this case, this particular area right here, this particular value, is going to be equal to minus 1.961. If we wanted to find the upper critical value in this case for using Excel, we would type in 0.9753184. What Excel is doing is it's calculating the cumulative probability up to this point. And remember that the area under the curve must equal 1. So here, given symmetry, it's very straightforward, it's positive 1.961. All right. So the last thing we need to do is compare our test statistic to our critical values. And what we see here is that our test statistic is 1.119. It's not more extreme than our critical values of positive or negative 1.961. And therefore, we do not have evidence to reject the null hypothesis in favor of the alternative. So we could conclude that the population average spending on office visits during the year equals $2,000. And what we observe is due to chance variation. So this concludes our example of a hypothesis test for a single population mean. Thank you.